Uh, Good morning, everyone. And I want to welcome you to my lecture today. Today, before I get started today, I want to make some announcements. Number one, I want to remind you Meetup 1 will be conducted on Friday in person at this venue. So the information about that and what you are expected to bring into the exam hall, please watch out today on the announcement section. I'm actually going to make an announcement about what you're going to bring into the exam. And today, as usual, I'm not going to have a review or a preview on assignment 4, but I'm going to make a video because I have a lot to do today. So I'm going to make a video, and I will advise that you check the Canvas today for the video on clarification on assignment. Okay, today I'm actually going to start from where we stopped on Monday before we go into the material for today. On Monday, of course, we introduced you to what we call the model complexity and model fitness. And of course, the criteria we use for model fitness and the criteria we use for model, both model fitness and model complexity. And of course, I walk you through different kind of criteria for model fitness. I talk about residual sum of squared and R squared. And I told you that the two of them, they are not going to be appropriate when we talk about model complexity. And of course, the criteria we normally want to use when we're going to put into consideration model fitness and model complexity. There are 3 of them. Number 1 is adjusted R squared. Number 2 is the AIC. And number 3 is the BIC. And of course, I also walk you through the method of selecting variables into model. And of course, I walk you through what we call the off-subset selection. And I also walk you through what we call the stepwise regression. But you know what I want to walk you, or what I want to do with you today? I actually want to start with how to implement that in R. Now, the first word that we want to talk about is what we call the off-subset selection. Okay, how do we do that in R? You're actually going to install a package called LEAPS. Okay, LEAPS. Okay, you load it. Now, I want to walk you through one example now. For instance, we actually want to predict quality of a professor based on some variables, predictive variables like clarity, the radar interest, paper, and the gender. Okay, we actually want to use a data set called Rate My Professor. I don't know whether you guys have come across that on the internet, where students actually provide a feedback about, the way professors handle their class. And you know what, the response variable here is actually quality. And we have some predictor variable, and we actually want to we're looking for the best statistical model that can actually be used to explain variables, predictor variables that could tell us about the clarity, about the quality of a professor. And you know what? We now want to consider all subset selection. And I'm gonna tell you the meaning. Now, when you do that, this is a code. I wanted to see what we get right now. You're basically gonna see what this is telling you now. I wanted to pay attention to this now. Information here, if you take a look at this, it's trying to tell you, if you look at in row 1, it's trying to tell you if you want to fit a simple linear regression model with only one predictor, then the best model out of or simple linear regression model is when we use clarity. That's why you see a star on the clarity. Okay, that is what it's trying to tell you. I'm going to say that again. You have so many predictor variables, but what this guy is trying to tell you now, if you decide to fit a simple linear regression model, because they're going to be 4 possible simple linear regression model, because you could look at the effect of clarity on quality, You could also look at the effect of rate of interest on quality. You could look at the effect of PPS on quality. You could look at the effect of gender male on quality. Okay, which means you got 4 possible simple linear regression model. But what this guy is trying to tell you now, among those 4 simple linear regression model, the best among them is the one with clarity. Now let me go to step 2. What is step 2 is trying to tell you? If you want to fit a model with only 2 predictors, okay, then it's trying to tell you the best combination is basically going to be clarity and rate of interest. And that was why you have a style on clarity, you have a style of rate of interest. And another, if you look at the row 3, if you want to fit regression model with 3 predictors, okay, based on this data set that we have, then it said the best one is basically going to be the one that have clarity, rate of interest, and PPS as a predictor. Of course, if you want to use all of them, what is the maximum numbers of predictors that we have? It's 4. Then that's why you see star on all of them. If you want to use all of them, then all of them is fine. So if you take a look at this all subset selection cannot give you the best model in all. It's only going to give you what is the best when I fit 1 predictor, what is the best when I fit 2 predictors, what is the best when I fit 3 predictors, and so on like that. That is what the off subset selection is going to tell you. Okay, now, but you know what? The off subset selection, we enable you, to narrow down. Now you know some important, some competing models now. It's going to be for one predictor is going to be the one where you have a clarity alone. For 2 predictor, where you have the clarity and rate of interest. For 3 predictors, so which means this particular method of selection actually suggested how many models? 4 models. Number 1, the one with the best predictor, the one with the 1 best predictor, the one with 2 best predictor, the one with 3 best predictor, and the last one, and the 4. Okay. Now, because of that, you know what we want to do now? These are the models suggested by the off subset selection. But you know what? We can actually go further using model selection with the AIC. Okay, when you take a look at that now, okay, a model, LM, quality, okay, on clarity, okay, and I want to extract the AIC. Why is it that K equal to 2? Okay, K equal to 2, that's for AIC, right? You remember I told you the other time? K equal to log of N, you can see 366. It means 366 students rated their professor. The sample size is 366. Okay, so I want to extract my AIC. I also want to extract my BIC. Okay, now when I do that for that, okay, I also repeat the same for each of the model. I repeat the same for each of the model. Where do I get these 4 models? Where do I get 1, 2, 3, 4? I actually got that 4 models from the all subset selection. Okay, which means this is step 1. The all subset selection will basically, give you the idea of what is the best 1 predictor, the best 2 predictor, the best 3 predictor, and so on like that. Then you're going to have something to work with. Now, what you're going to do now, then you're going to fit that, okay, where you want to extract the AIC and the BIC of all the 4 models. Oh my God, compare the AIC now. The model that we're actually going to choose at the end of the day is the one that have the lowest AIC. Take a look at that. Okay, now that is how all subset selection work. Now, the next thing that we want to talk about is what we call a stepwise regression. The stepwise method, I explained the basic principle behind that last Monday, right? Where I walk you through what we call a backward elimination and a forward selection. Now, if you take a look at, what you're going to do, if I want to do backward elimination, I'm going to state all the model. I'm going to state the model. I'm going to start from the complicated model. Oh my God, backwards elimination. I'm going to be going backward and I'm going to be eliminating predictor. It means I'm starting with a complicated one. Oh my, look at that. 1 plus clarity, radar interest, perfect gender. I'm starting with the most complicated model. Then I'm going to write step into M4 that, and I'm actually going to indicate in the direction. I'm going to indicate backward. Look at that, in the direction, backward. You know what's going to happen? Automatically, the arrow will generate the best model for you. Look at the best model it's generating now. The best model is actually generating now is a model with clarity and rate of interest. That's as simple as that. That's what it's generating now. Okay. And this is going to save your time compared to all subset selection, because in the all subset selection, it's going to be a 2-stage. Okay. In the first stage, you figure out what is the best among 1 predictor, among 2 predictor, among 3 predictor, among 4 predictor. Then from there, you're going to go and look at the AIC, compare the AIC. That's a 2-stage, right? But here, just from 1 stage with 1 code, it's going to give you the best model. Now, if you want to do the forward, this is a code. You're only going to change. If you want to go with the forward, you are not going to start with a complicated model. You're actually going to start with an intercept model because you want to be going forward and you're going to start with nothing. When you start with nothing, which is what we call intercept, right? Intercept model, right? No predictor, right? Then you're going to be adding. That means you're going to start from the intercept model. That was why we call fit simplest model, where you have quality on 1. Then you're going to indicate direction equal to forward. Take a look at that. Then this is the model suggested. Now you can see here, it's looking as if there is an agreement between the forward and backward for this data set, because they all the 2 of them actually pointed towards the same model. Let's see whether there's let's see what the offset selection actually, based on the AIC here, the one with the smallest AIC, of course, is the same. Is this guy here? Look at that. That is the smallest AIC, right? Take a look at that. So which means the 3 of them agree on having clarity and rate interest to predict the quality of a professor. Look at that. They all agree. Okay. Now, on the bootstrap for regression, I'm going to skip that for today because of my time. Okay. I'm going to skip this for today. So because of my time, I'm going to talk about the bootstrap for regression later. Okay. Let me stop my share. I'm going to go into the material for today. Give me 1 second. Give me 1 second. You're going to see that now. Okay. Those of you online, can you confirm if you're seeing what I just project right now? So if you're online?
Yes.
Okay. Do you see multicollinearity, right?
Yeah.
Yes.
Okay. And let me check. Is it changing for you? I just want to see. Is it changing, right?
Yes.
Okay. Thank you so much. Thank you for confirming that. I want to welcome everyone into today's topic. This topic is very, very important within the statistical framework and data science anywhere in the world. So I wanted to pay attention to this. Now, statistics is like a story that goes on and on and on. We started by trying to characterize relationship between variables, 1 predictor or 1 response. We fitted a simple linear regression model. And you know what? The specification of linear regression model actually come with assumptions. You know that, right? Assumptions of linearity, normality, constant variance, the absence of unusual observation, like outlier, high leverage. And we now realize that at times we could have situations where we needed more than one predictor, okay, in the model. Because of that, we actually consider what we call multiple linear regression, right? We are a situation where we believe, more than one predictor variable is actually going to explain the response. And not only that, we believe at times that, okay, the relationship between the response and the predictor may not be linear, may even be non-linear, maybe quadratic or cubic. And you know what, based on what we did before, we actually incorporated, in addition to the linear effect in the model, we incorporated what we call the quadratic effect and the cubic effect. And even not only that, I've also walked you through a situation whereby you needed to test the effect of interaction. I remember when I was trying to investigate the effects of a dose of drug on anxiety, on how to reduce anxiety. And I said, if the drug actually have different effect on male and female, then of course you actually need to incorporate the interaction effect of a gender and the dose of drug into the model. Okay, why are we doing that? Why are we actually incorporating a nonlinear effect into a linear model? Why are we incorporating the quadratic effect? Why are we incorporating the cubic effect? Why do we need to have, why do we need to incorporate the interaction effect? We are trying to do that with the intention of improving the performance of our model. That's why we're doing that. But let me tell you this. When we are trying to solve a problem, we create a new problem. And I want to tell you today, when you incorporate a quadratic effect into your model, or cubic effect, or an interaction effect into your model, it's basically going to lead to another problem that you actually need to address, which we call multicollinearity. Now, let me tell you, what do we mean by multicollinearity? Multicollinearity is when the independent variables, the predictor variables, they correlate. We expect them to be truly independent, but situation where they are not independent, okay, the situation where a particular predictor variable actually depends on another predictor variable, that's going to be a problem. Okay, and you know what? If you take a look at what we did, if I have y equal to beta naught plus beta 1 or plus that and this, of course, you're basically going to see that this guy depend on this guy. S squared depend on S, right? You know that, right? They're actually going to have relationship. And you know what? When they have relationship, because one of the additional assumption, of a multiple linear regression is that the predictor variable should not correlate. But you know what? There is no way you can actually, prevent that, from happening when you are trying to fit this kind of model, because the S square here depend on S. This particular guy here depending on this guy. And you know what? When you are trying to solve one problem, you are creating a new one. Okay, and that is what we call multicollinearity. So because of that, today I'm actually going to walk you through how do you identify multicollinearity in regression, and how do you now understand the effects of multicollinearity on regression model, and how do we fix it? Okay, that's what I'm going to walk you through today. Now, like I said, I've told you what the multicollinearity means. When you have a situation where variables, the predictor variables, they correlate. They shouldn't correlate. That's an assumption. Okay. Let me also tell you this. In addition to linearity, assumption, normality, okay, assumption, constant variance, assumption, okay, assumptions of absence of unusual observation, like outlier, high leverage, okay, for multiple linear regression. Another assumption is that the predictor variable should not correlate. Okay, when they do, what happens? When they correlate, you know what is going to happen? You cannot trust your p-value anymore. You remember when you want to find, when you want to investigate the effects of a particular predictor, right? In a model, you know what you're going to do, right? You're going to conduct a t-test, right? Now, when multicollinearity exists, you cannot trust your p-value. Okay, on a normal ground, a predictor that's supposed to be significant, okay, when the multicollinearity exists, that predictor will not be significant, even though if other assumptions hold. Okay, and that is why at times don't celebrate. You know, at times in research, we normally celebrate very quickly. Okay, we celebrate in a hurry. We shouldn't be rushed to celebrate. Okay, before we can actually celebrate success, okay, what we actually need to do, okay, we need to investigate whether all assumptions hold, including the assumptions of multicollinearity. Okay, because you know why? If you don't take care of multicollinearity, it will actually reduce, okay, the precision of the estimated regression parameters. And when the precision is very low, you know what happened to that model? The model will have low statistical power. It's going to have low statistical power. When you base your policy formulation on such model, you're actually going to mislead. Okay? Okay, you're actually going to mislead. Okay, now, how problematic is multicollinearity? You know, we have the moderate and we have the severe. The moderate one, okay, we can still tolerate that, but the severe one, we can, you know, it's actually going to change the decision. And let me tell you this. What are you going to see in a model when you fit a model? What are you going to see before you can actually say there's a multicollinearity problem? Now, let me start by demonstrating this. Now, I wanted to focus the board right now. Now, this is what happened. You know, when you run a model, maybe a linear regression model, maybe you run Y on X1 plus X2 plus S3, and you did a summary, okay? You did a summary of the model. You know, you normally have estimates, okay? You have estimate, standard error, okay? Standard error, t-value, and you have p-value, right? You know, this is what you normally have, right? When you run linear regression, right? You're gonna have some values here, right? Okay, let me tell you this. When multicollinearity exists, it will inflate the variance. Inflate the variance. Now, the variance of what? If you take a look at this guy, the standard error here, the values we have under the standard error, okay, is very, very crucial. You know why it is crucial? If I want to get a t-value here, okay, for instance, if I want to talk about beta 1, maybe I want to get a t-value for a particular beta, you know, it's going to be estimate of that divided by the standard error. Okay, now what I'm trying to talk about now, when multicollinearity exists, the standard error here is going to be so large. You know why it is large? It is large because the variance of the standard error, the variance is large. When the variance is very large, okay, you know, you're going to get a standard error from the variance by doing what? The standard error of that is the square root of the variance. Okay, so situation when the multicollinearity exists, the variance will be inflated. And when the variance is inflated, what happens to the standard error? The standard error is also going to be large. Now, I wanted to look at it mathematically now. When the standard error is large, when the denominator of a fraction is very large, what will happen to t? This very t here will tend to 0, right? You know that the t will be very small, okay? When your t value is very small, you know what is going to happen to the p value? The p value will be very large. When your t value, or your test statistic value is very, very small, okay? Your p value will be very large. When your p-value is very large, you know the implication, right? You're going to fail to reject the null hypothesis. What are you testing? You're testing this guy here. When you fail to reject the null hypothesis, you know what that means? It means that particular predictor is not significant. And maybe it should be significant. But the reason why it is not significant is because of the fact that the model has a multicollinearity problem. Maybe some variables are correlating, and that is why that happened. Okay, and let me tell you this. Now, the consequence of multicollinearity is that you cannot trust your standard error anymore. And if you cannot trust your standard error, then because you know the meaning of the standard error here. The standard error tells us how reliable is the estimate. How reliable. Okay, that is what the standard error tells us. Okay, and when the variance is inflated, that will affect the standard error. And when that affects the standard error, then it means you cannot actually rely on your estimate. And you know what? The t-value is not going to be appropriate, and your p-value you cannot trust. Your p-value. Okay, and what is another consequence of that? You know, another thing you need to suspect when the multicollinearity exists. Okay, maybe you are expecting a positive sign. You know, maybe looking at the regression that you conduct, maybe you are looking at a y of equal to beta null plus beta 1s. I'm going to give you one example now. If y is winning percentage of a particular football league, and if x is touchdown, numbers of touchdown, oh my God, you know how they play the football that they're going to have a touchdown. You know, the more touchdown they have, then the more the chance of winning. You know that, right? Now, what do you expect? You expect the sign to be positive, right? You expect the sign of the beta 1 to be positive. If a multicollinearity exists, it's going to switch the sign from positive to negative. Okay? So situation where you have unexpected sign, okay, then there's a multicollinearity problem. So we need to pay a lot of attention. Okay. Now, I've just discussed the consequences of multicollinearity, that you cannot trust your p-value anymore. Okay, even though you are supposed to have a significant result, it's going to tell you it's not significant. And the reason why it's saying that is because the variance is very large, and that affects the standard error. And when the standard error is very large, then the t-value will be very small. And when the t-value is very small, the p-value will be very large. And when p-value is very large, compared to the level of significance, you're going to fail to reject the null hypothesis. And let me tell you this, even though the f-test that you conduct may be very high, the p-value associated with the f-test will be very, very small, giving you indication that everything is right. But you know what? Everything is not right. Okay. How do we fix it? You know, I told you the other time, there's always going to be a problem, old problem, new problem, but I'm not worried about that. You know, what I just worry about is how do I fix the problem when problem arrives? How do we fix multicollinearity problem? We have a lot of suggestions doing that. Number one, we can actually remove a variable that is causing the problem. Okay, we need to identify a correlated variable. I know there's going to be a particular predictor variable causing the problem. I'm actually going to demonstrate that to you today. Now, another way is to standardize, because at times, it is not all the time we remove. What if the variable is very, very important? What if the variable has a very strong statistical backing or theoretical backing that it should be in the model? Okay, like in the case of interaction. Okay, we know that, there's a situation where we needed to incorporate interaction in the model. If one of the variable, okay, that are in the interaction is causing the problem. If you remove it, then it means you are no longer going to test your interlaction effect. And that is not going to be appropriate. How do we actually accommodate that? Then we can standardize. Okay, standardization. Standardization does not have to do with removing a variable. Okay, I'm going to walk you through that as well. Or you can run a different analysis. There's something that we call principal component analysis. Okay, and there's something that we call ridge regression, lasso regression. They're different kind of, depending on your, because that's going to be above the scope of this level. I may not be able to talk about that, but we have, alternative way to handle that. Okay, but I want to walk you through this example now, and I want you to pay attention. We're trying to look at the variables that determine the numbers of doctors. Okay, we want to determine the numbers of doctors, and we come across numbers of hospitals, the numbers of beds in the hospital, and interaction effect, because the relationship between hospital and doctors could depend on the numbers of beds. I'm going to say that again. The relationship between number of hospitals and the numbers of doctors, the relationship between them may depend on the numbers of beds, and that is why we are incorporating the interaction effect. Look at that, hospital and bed in the model. When you take a look at this, you're basically going to see that the model, as we have already solved, we've already investigated assumptions. This model, initially when we fitted numbers of doctors against that, there was a violation of linearity, constant variance, and so on. But you know what? We solved the problem by taking the square root of the numbers of doctors. You remember transformation, right? We took the square root of numbers of doctors. That solved the problem. But you know what? That transformation does not solve multicollinearity problem. How do I know? When you run your model, if you want to know, you actually, if your model, okay, if your model equal ln into y, okay, square root of y, numbers of doctors on hospital plus bed, okay, plus the interaction, okay, when you run this, if you want to know, okay, you just do VIF. VIF into model. VIF means variance inflated factor. We got a threshold for the VIF. If the VIF of a particular predictor is greater than 5, then it's going to be problematic. I'm going to say that again. When your VIF is greater than 5, that will be problematic. Now, take a look at that. The VIF of hospital, of bed, of the interaction, what happened to the each VIF? They are all greater than 5, and that sends a multicollinearity problem. But look at another thing that we see here. You're actually going to see that if you look at the p-value, all of them, they are actually significant. Look at that. Look at the p-value. And you're going to be celebrating. Oh, they are significant. Oh, my God. Don't celebrate yet. Look at the VIF. And this is a code. You got a VIF into your model. It's going to return the VIF for each. And we got a threshold. The moment it is more than 5, then it's going to be problematic. Okay? Then I'm going to walk you through another example that you like. You're going to see now. I want you to pay attention to this. Okay? We want to look at the effect of some predictor variable on the winning percentage of a football league. Okay? For instance, the important variables are 0.4, point against, yard for, and touchdown. Those are the predictors, right? Now, when I run the regression, oh my God, look at the p-value. It's telling me 0.4 is insignificant. Oh my God, that doesn't make sense. 0.4, what increase the chance of winning is when you increase number of 0.4. Then another one, oh, look at touchdown. Can you see the touchdown? Look at the p-value associated with the touchdown. It's telling me it's not significant. And from the theoretical situation, we expect touchdown to be significant. You know why? Why that is not significant? Because there is a multicollinearity problem. And you're going to see here, offensive regression parameters are not significant. Those ones that are significant is defensive here. Look at that. Defensive point against, because the p-value is significant. But when you look at the offensive one, they are not. There's a problem. And what am I going to do? I'm going to run a VIF of the model. And when I run the VIF of the model, look at that. Okay, our touchdown has a VIF of 16.47. And let me tell you why. Touchdown and 0.4, they could correlate. Because 0.4 depend on the number of touchdowns. And that is the reason why in this model, there's a multicollinearity problem, because they are related. Okay, and we don't expect predictor variable to depend on each other. We don't expect that. So we realize that using the touchdown, okay, and you use the touchdown, okay, and 0.4 in this model, they basically they're going to correlate, and when they correlate, there will be multicollinearity problem. Okay, and because of that, we are not going to trust the p-value, and the only way to know whether there's a multicollinearity problem is to get the VIF, and the threshold is when the VIF is greater than 5, then you're actually going to conclude that you'll be able to identify the variable that is problematic. Okay, now, and let me tell you this. Look at the p-value of the overall test. Even the p-value of the overall significance of the model is even telling us everything is fine when everything is not fine. Look at that. The p-value of 0.00, okay, is telling us, oh, everything is fine, but everything is not fine. Look at the R squared and the adjusted R squared. They are even very high. That doesn't matter. Multicollinearity could exist in the model, and the R squared and the adjusted R squared are very high. We cannot trust them. Okay. Now, if you want to base, let me tell you this. Before, we've done what we call partial F-test, right? Now, if you want to really see, what this analysis is telling us, what this result is telling us, is that, okay, 0.4 is not significant, yard 4 is not significant, touchdown is not significant. That is what it's telling us, right? If you really want to investigate whether they are significant or not, you can conduct a partial F-test. What am I putting to 0? What is the beta 1? The beta 1 is the slope. The beta 1 is the slope for 0.4. Okay. The beta the beta 3 is the slope for yard 4, and the beta 5 is the slope for touchdown. Okay. I want to conduct a partial F-test between this and that. You know what I'm trying to say? If you look at the first model, okay, because what that very result is telling me, I should only use point against and yard against, because they are the only significant predictor. Okay, and then I want to compare using point against and yard against only, or using the everything. Look at that, using the complicated model. We've done that before, right? Partial F-test. What happened now? Look at the p-value. Okay, the p-value is very, very small. What is the meaning? It's telling you reject the non-hypothesis. It's trying to say, no, the simple model is not appropriate. You need to use the complicated model. And therefore, we have justified that in our model, we needed to have touchdown, 0.4, and yard 4. Okay, so this is a justification for that. Okay, now I want to give you another example. I'm going into politics now. Okay. I want to predict whether countries with the high levels of clientelism, what I mean by clientelism is just like, that is the exchange of goods and service for political support. We have some governments that actually do that. Okay, and I'm trying to look at the effect of that high levels of vote buying and low democracy score on the executive embezzlement. Okay, I want to look at the effect of that. Okay, when you're running, I have this result. Okay, when you take a look at this result, okay, the clientelism and vote buying, they are related. Now, because they are related, okay, we do not expect. You can see here the clientelism index is not significant. I did not start that. With the one I star, the one I have star is the one that is significant. Okay, and the reason why that happened is because it's actually correlating with vote buying score. Okay, even though look at the R squared, look at the F statistic. Okay, it's telling us a different result. Now, what I decided to do, I get a VIF of all of that to be able to see. But the VIF of this guy and the vote buying, they are more than 5. One of them has to go. Okay, if I really want to drop, like if I told you the other time how to fix one of the way to fix multicollinearity is actually to drop a problematic predictor variable. Now, when I drop vote buying, okay, and I run the regression, then I realize that when I drop vote buying and I run the regression and I realize that everything now looks good. Okay, but let me tell you, you can calculate your VIF again and see none of the predictor now, it's more than 5. It means everything is 5. Everything is fine. So the only way you can investigate, you can just look at the VIF. Now, I told you the other time, it is not all the time that we remove. What if there's a strong theoretical backing for the particular variable that we are not going to remove, like an interaction? Then I'm going to walk you through the method of standardization. Now, I want to take a look at this result. We want to look at the effect of fat, weight, okay, activity, and as well as the interaction of fat and weight on the femoral neck. Okay, now I wanted to pay attention to the p-value here. It's trying to tell me fat is not significant because the p-value is 0.176, is greater than 0.05. Okay, now how come fat is not significant, but the interaction between fat and weight is significant? It doesn't make sense. Before an interaction can be significant, we expect one of the components of that to be significant. But when you take a look at this now, okay, in fact, look at that, the interaction is significant, 0.05, but when you take a look at the fat, it's not significant. Now, when we suspect that, you know what we're going to do? We can get a VIF. Oh my God, look at the VIF of each predictor. They are, 3 of them. They are above 5 threshold. Okay. And you know what? All these predictors have to be in the model. We don't want to remove. In that kind of situation, then we need to standardize. How do we standardize? We find the mean of each predictor, then we start subtracting. Okay, there's something that we call the deviation. You calculate the deviations. Okay, you get a new variable. You divide by the standard deviation. You get a new variable. Then you now rerun that. Now, let me show you. After rerunning that, after standardization, look at what we have. What happened now? After standardization, all of them are significant. Look at that. And when I recalculate the VIF, after standardization, none of them is up to 5. The threshold, none of them is up to 5. Look at that. Now, to fix multicollinearity problem, at time we remove the problematic predator, and at time we don't remove if it has a theoretical backing to be included in the model, then we're going to go for standardization. Now, let me tell you another approach used by data scientists. The another approach used by data scientists is they're going to fit what they call lasso regression. There's something that we call lasso. You know what lasso is going to do? Lasso regression. If I have so many predictor variables that correlate, you know what lasso regression is going to do? The lasso regression, those variables that may be problematic, the lasso regression will eliminate them. You're not going to see them in the output. It's going to shrink their parameter to 0. Okay, so we use lasso regression, to solve the problem of multicollinearity. And not only that, situation where you have high dimensional data, where you have a lot of variables, like in gene sequencing, in some time series analysis, and so like that, where you have it in big data. There's something like in big data analysis, big data. Okay, big data. Okay, where we have thousands of predictor variables. They have a tendency of correlating because there are so many of them. We can fit lasso regression. The lasso regression is just going to return those predictor variables that have effects that are not problematic. It's actually going to shrink, the estimate, the parameter estimate of those predictor variables that are not important, that could be problematic, to 0. But you know what? The method I've actually walked you through today on how to face a multicollinearity problem is how you can drop a problematic variable. You look at the VIF, the one that have the highest values of VIF is probably going to be the one that is actually causing the problem. And another way, if the variable has a theoretical backing to be included in the model, then if you cannot remove it, then you need to use the method of standardization. Okay, with the method of standardization, of course, and you rerun your model, you're basically going to say that you fix the problem, and how you're going to investigate whether you fix the problem is to find the VIF again. Okay, and when you find the VIF, and if each of them is less than 5, okay, then you're going to say, okay, everything is fine now. Okay, I can trust my p-value now. Okay, I can go ahead making my decision now. Let me tell you this. At times, it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. Now, before I go today, you're going to be having a midtime 1 on Friday at this venue. I want you to go back to the midtime 1 practice question. Okay, study that. Get yourself familiar with the midtime 1 practice question. And the exam is going to be centered, the area of coverage is going to be chapter 0, 1, and 2. Okay. Believe in yourself that you can succeed, even if you have not had A before. Who tells you that you cannot get A? Believe in yourself that you can do it. You only need to figure out, you need to take your time, what you need to do. Have confidence in yourself. Okay. Just take your time, study, get yourself familiar with the midtime 1 practice question before you're going to score 100%. Even if you have not scored up to that before in any statisticals. But this time around, tell yourself, even though you are in the middle of a difficult situation right now, I understand, but I face the situation as well. Blood runs through my vein. I am a human being. I know what is going on. But against all odds, you tell yourself, I'm actually going to succeed. You got no choice. You will succeed. Okay? So I'm going to see you on Friday for the test. Make sure you stay safe and have a very beautiful day. Okay, thank you too. Bye for now.